a material, you will get into smaller particles. And as you keep on breaking, finally you reach a stage where you cannot break them any further. And that point, when you reach the limit that you reach, where no further breaking is possible, that is called the atom. Beyond that, you cannot. This is one part. There was another part of it, and that part of it is that while you keep on breaking and arrive at the atom, atoms of different elements are different. That is, atom of hydrogen is different, atom of helium would be different, and so on and so forth. The third part that came up is that we have molecules, and the molecules are composed of combination of atoms. That is, the most well-known example is water. Two atoms of hydrogen and one atom of oxygen, they join together, combine together, and they form a water molecule. This water molecule is formed through a chemical reaction, and such kind of chemical reactions, we call them as synthesis. If you separate out atoms and molecules, we call them analysis. That is, if you heat water to a very high temperature, it can again break into its constituents like hydrogen and oxygen. And when that happens, we will call it a process of analysis. That is, by which you break it into smaller parts. And other than that, when they combine, these are called when they combine, these are called synthetic reactions. Once this was done, it was also found that these atoms can have their different, analysis, and other is called synthesis. So it was also found that these atoms have their different atomic masses. Molecules, if you take, they have their different masses, and so on. These atoms and molecules ideas were used to understand the properties of gases. So gases have certain properties, and that is called the gas laws. That is, pressure, if the amount of gas is a constant, if you fill a jar with a gas, try to measure its temperature, pressure, and volume. All these things you try to measure. Then you will come across a relationship that pressure multiplied by the volume is going to be proportional to the temperature. These are called the gas laws. Now, how do these gas laws come about? How to understand how these gas laws come about? In order to do that, it was understood that a gas is composed of atoms or molecules, and they move about at random. Once they come and hit at a surface of the wall of the container, it is here that it transfers its momentum to the wall and is reflected back, rebounds back, and as it rebounds back, there is a change in momentum. It is like this. It was coming in this direction, and now it has gone backward in this direction. So whenever there is a change in momentum, there is a force. A force is a cause, and this force is transferred to the wall of the container, and force per unit area we know is pressure. That's how pressure comes. How does temperature come? How rapidly these gases are moving, that will finally determine what is the temperature. So all these were known, and once all these were known, people tried to understand other features of the gases. But this idea of gases, this idea could not explain to us anything about how a gas can be liquefied. So this was not understood. People in the beginning had thought that if you apply pressure, gas will finally get liquefied. Finally, but it was found, no. Just by applying a pressure, you cannot liquefy a gas. You have to lower the temperature also at the same time. And unless you're below a critical temperature, no gas can ever be liquefied. Why is it so? We know the gases are composed of atoms. All this happened. Finally, the explanation the for the for liquefaction, or why it is possible to liquefy finally, is this: that gases have a finite size. All this time, in all these theories, it was determined that the gases size is zero. The size, the volume, the gas atom does not occupy any volume. But that was not true. And there was a scientist, his name was Van der Waals. He said, no, we cannot assume the gas atoms or gas molecules to be of zero volume. They should have, no matter how small, they should have a finite volume. And when you put that in your theory, you could find that yes, a liquefaction of gases is possible, and your theory predicts it. Well, we have understood that yes, gases have a finite size. How to determine that? So that determination had to wait for some time. And one of the persons who gave a method by which the sizes of gas molecules or gas atoms could be found is a theory which was given by Albert Einstein. It is called the theory of the Brownian motion.
Can I ask you one
And,
question?
and that is how, yes, please, Ibrahim has joined, or he wants to ask something. Okay.
Can I ask you a question? Can all the elements in the periodic table, 118 of them, can be turned into gas, liquid, and gas, liquid, and solid?
Yes, but that would depend upon temperature and the pressure. It is not that everything is a gas at all temperatures. It is not that everything is a liquid at all temperatures. It depends upon temperature. Like hydrogen is a gas, and I think it's, in order to liquefy hydrogen, you have to go to very low temperature, minus maybe, I don't know, remember the exact number, maybe minus 240 degrees centigrade. You have to go. Please check this number. So it depends upon the temperature, and the gas which refused to be liquefied. We could not liquefy it at all. And people believed that maybe this gas can never be liquefied. That was helium. And helium could finally be liquefied. Maybe it is about 110 years ago. Liquefaction of helium was done, and that temperature is minus, I would say, how much? Minus 269 degrees. You have to cool it. You have to minus 269 degrees centigrade. Only then helium could be liquefied. And why is it so? These, finally we will find, these also have to do with certain things called like the quantum properties of matter. Quantum properties of matter. Okay, these have to do with the quantum properties of matter. So one thing we have come across, that yes, that gases could be liquefied, and gases gases can be liquefied, and this liquefaction has to be determined by the sizes of these molecules. But there has to be not the sizes alone. It has to include another part in it. Earlier, no, we deal everything with not degrees Fahrenheit, generally with the Celsius or degree centigrade. And there's another scale of temperature, we call it the absolute scale of temperature. So absolute scale of temperature begins with minus 273 degrees centigrade. Absolute, that is called the absolute scale of temperature. We call it the absolute zero. Okay. So gas laws, when I said Boyle's law, Charles' law, we deal with absolute scale of temperature. Now here also comes the problem that certain substance that, yes, degrees Kelvin, we call also degrees Kelvin. Kelvin is the scientist, and after his name, this is done. So the idea is this, or rather, I would say the question was this: that here are gases, and in order that they be liquefied, the gases or atoms should have a finite volume. How small they should be, you can make a small calculation yourself. Suppose I consider that gases are in the form of a sphere, then the volume of any sphere is 4 pi by 3, 4 multiplied by pi divided by 3, and this whole quantity is to be multiplied by radius to the power 3. That is we know that is the formula for volume. And this formula for volume, if you put, last time I had, or some time back, I had told that the radius of a hydrogen atom is 0.52 into 10 to the power minus 8 centimeters. Okay. So you can calculate what this volume is going to be. So volume of a hydrogen atom is going to be 0.5 to the power 3 multiplied by 10 to the power minus 24 centimeter cube. It is a very, very tiny number. Very, very tiny number. True, it is very small, but unless you consider this small volume, you cannot understand that there are that gases can become liquid. This is one part, but that is not alone. That is, all this time we had considered that these gas molecules, as they move about, they do not interact with each other. That is, they cannot collide with each other and change their paths. That is not true. Their only collision takes place with the wall. That also is found to be not true. That as they move about, they collide with each other. And while they collide, as long as they come close to each other, up to a certain distance, they may attract. But beyond a certain distance, they are just pushed away from each other. And of course, this I'm talking in terms of non-reactive gases, the gases which would not react to each other. So there are two immediate points came up, that atoms do have a finite volume. That's one part. And secondly, when two atoms come close to each other, initially they can approach each other, but beyond a certain point, they're pushed away from each other. So what is it that leads to this? What is it that in the composition of matter itself that is leading to these phenomena? This became a question which could not be answered. So we stop at one level. As I said, the story is never the story that goes in a straight line. The story of science never goes in the form of a straight line. And once we stop there, it remained like that for long. Then in the year 1897, the discovery of the electron took place. It was done by Sir J.J. Thomson. And with the discovery of the electron, there comes another question, that inside, since an atom is electrically neutral, so there must be a positive charge inside. And finally, with the famous alpha scattering experiments, Lord Rutherford could show that yes, that there is a positive charge, but this positive charge is concentrated in a very, very small volume, which we call the nucleus. Which means most of the atom is actually empty. Most of it is empty. It is only at the center that there is something called a nucleus, which is the point where uh, uh, all the positive charges concentrate. And how much are these positive charges? Let us see. Hydrogen has only one proton, so we measure from now onwards. The measurement for the charge will be in terms of number of electronic charge. So hydrogen has a single proton, so therefore we denote by small e the charge of an electron. So electron and proton have the same charge, but only the signs are different. Magnitude of the charge is the same. So therefore with hydrogen, with one proton only, there is plus e. When we go to helium, it becomes twice e. Lithium, it becomes thrice e. Beryllium, 4, 5, 6. Carbon becomes 6e. Nitrogen, 7e. Oxygen, 8e, and so on and so forth. Uranium, it will become 92e, and so on. So it goes on. And as it goes on, the question is that comes up when we apply Bohr's theory of the atom. Niels Bohr, if you recall, he immediately came to the conclusion that if there's a positive charge there and a negative charge outside, the attractive force of these two will make the negative charge, that is the electron, move in orbits. So these are like orbits around the nucleus that they go around. And these orbits are going to be different orbits because two electrons cannot be in the same orbit because they would collide with each other and they will repel each other. So there are going to be different orbits. And he told that how an idea of the quantum world, that not all possible orbits are possible, but there are only certain orbits are possible, and these orbits have to be determined by this particular formula. And the formula is multiply the radius of the orbit, with the mass of the electron, with the orbital velocity of the electron. If you consider this product, we call this product as action. In scientific term, this multiplication of length multiplied by momentum. Momentum is mass multiplied by velocity. That is momentum. So mass multiplied by velocity is called the momentum. So the rule that Niels Bohr said, that only those orbits are possible inside the atom such that its circumference multiplied by the orbital momentum is equal to an integer number multiplied by a constant called the Planck's constant. And this Planck's constant, is denoted by the letter small h. Small h, so the nh. So therefore it will be 2 pi r multiplied by m into v is equal to n multiplied by h. This h is a constant which describes the quantum properties. That is, whenever an energy transfer of radiation takes place, that is, whenever light transfers energy, it does not transfer it continuously, but it transfers into small steps. And in every step, the amount of energy that can be transferred is equal to h multiplied by the frequency of the light. And since it is not a continuous process, but indefinite small quantities, that is how the name came up as a quantum. So every time we transfer energy, transfer energy, h into nu, we are transferring one, one quantum, yes, one quantum of energy. So one quantum, we can two quanta, three quanta, four quanta, five quanta, something like that. It is something like this, that when we make right, when we, as I gave the example last time, that when we drink water, we don't, we can't say that how much water we are drinking. We only say one glass of water. But you can also drink half a glass of water. You can also drink 1/4 glass of water. Yes, any fractional things are possible. Fine. But that is not possible when light is transferred. It is not like that it is half a quanta is not, cannot be transferred. 1/3 of a quantum is not possible. It has to be going as integer multiples of this quantum. You're sending one quantum, two quantum, three quantum, four quantum, and so on and so on. So this is how Niels Bohr introduced the quantum concept into the structure of atoms. Structure of atoms had to have this quantum concept in order that we could understand several properties of matter. One of the questions that would come immediately is that yes, we have developed this quantum concept, but with the help of this quantum concept, can we tell that what is going to be the radius of a hydrogen atom? We have put forward that the radius of the hydrogen atom has to be finite because hydrogen can be liquefied. So what is its radius? From different experiments, the radius of us was found to be, as I said, 0.5 into 52, roughly 0.52 into 10 to the power minus 8 centimeters. That is the radius of the hydrogen atom. Now the question is, with this Bohr's theory, can we predict what is going to be the hydrogen atom's radius? Predict in terms of what? What has come in the theory? It has come, it has needs the charge of the electron, which is measured, mass of the electron, which is measured, and it has got the Planck's constant, which is also measured. So all these three quantities are measured. And Bohr gave a scheme by which all these three quantities come and enter in determining the dynamics of electron inside the atom. So with those ideas, the question comes, let us put in the formula that Bohr has given about the radius of the hydrogen orbit. And that radius is going to be the size of the hydrogen atom. If you put all these, it completely matches. It completely matches with whatever we had known. Whatever experiments had shown, it completely matches. And the point that I would like to say again, that whenever we do science, it is not by imaginations alone, but this imagination and what we predict, they have to match with actually is found from experiments. And this is called the reality. With reality, we have to match our things. So, okay. Yes, please.
In this case, for hydrogen, the value of N is going to be 1 because you only have one electron.
You only have one electron. And why N is going to be 1? That is, that comes from the Bohr's quantum condition. There's only one electron.
Okay.
Okay. Hydrogen has only one electron, so it has to be only 1. N is equal to 1. So, so next comes, so now let us see. It has been given for hydrogen. It has to be given for other atoms also. if you keep on measuring these things, you come to a very strange condition. And the condition is the size of the orbit shrinks as the charge of the nucleus increases. The orbit size shrinks as the charge of the nucleus increases. And that is because as the charge of the nucleus increases, attraction on the electron also increases. It goes by inverse square law, which is called the Coulomb's law. So suppose the charge is Z into E. Z we call the atomic number. That is how many electrons are there in the atom, or how many protons are there in the nucleus. That is called the Z. We call it the atomic number. So as the atomic number increases, the force on the electron goes as Z multiplied by E, that is the charge of the nucleus, that multiplied by E, that's the charge of the electron, divided by the distance to the power 2. And this distance is the distance between the nucleus and the electron in its orbit. We are considering that all these orbits are going in circular fashion. So since that increases, there is a greater pull of the electron towards the nucleus as the atomic number of the electron of the atom increases, and that pull has to be counterpoised, or it has to be balanced by what we call the centripetal acceleration, which should take the objects away from it, away from this orbit. So it is because of this competition, higher the atomic number of the nucleus, smaller is going to be the size of the atoms. This is one part. So this is if hydrogen has only one electron, there has to be only one orbit. When you come to helium, there are two electrons. They also have to be put in two orbits, but these orbits can both have n equal to 1, because there is something, there's another, these are called quantum numbers. There are several quantum numbers had to be introduced. N is one such quantum number. N, that we said, it is called the principal quantum number. So several such quantum numbers had to be introduced to describe the entire structure of an atom. And every orbit for every electron, these kind of quantum numbers have to be satisfied. This is one part. So what are the quantum numbers? These are the details which will be much beyond the comprehension in school levels, but it is just for your information that I would like to tell that what are the quantum numbers. The quantum numbers, we have talked about the motion around the nucleus, that is one. Then question is, again, you can ask that yes, we have got the orbital motion, but is this orbital motion, all the orbits are going to be in one single plane, or there can be different planes? That is, one of them is going in this motion, another is going in this motion, and so on and so on. Okay. So this is another kind of quantum number that has to come in. So in what is the orientation? Orientation of these different planes, and yes, n into small h, please. Yes, not capital H. So one can be in this direction, another can be in this direction, another can be in this direction, and so on and so forth. Now, having said that all possible orbits are not possible, or any arbitrary orbits small h please for Planck constant. Okay, so the other thing is that the orbits are also cannot be inclined in any direction. If it will be one like this, then there has to another one, and in between there can be no other orbits. Again, in between there can be no other orbits. So there are not only the sizes of the orbits are important. The other thing that was decided is the inclination of the orbit. This inclination of the orbit becomes a point, and this inclination of the orbit should also be different. So these are what are called the quantum schemes. What is going to be the rotational velocity around the nucleus? That has to be only in very given definite numbers. It cannot be any arbitrary number. And again, what are going to be the planes of these motion? These also have to have a certain or has to have certain definite numbers. So this is one point. This is one point. But it has to match with other observations. And this is, again, with what observations to match? Well, strange it may seem, but science always takes us in strange directions. And people started thinking that we should now try to match all these observations with magnetic properties of these materials. And let us understand how this kind of scheme of things suddenly appears in the magnetic properties of material. In order to do that, we must go back again in history. And it was from about the year 1800 and so on that people knew that if you have a moving charge, which means an electric current, if you have, and if you put a magnetic needle close to this electric current, the magnetic needle deflects. Okay, magnetic needle deflects whenever we put it near an electric current. Following that, there was a scientist whose name was Ampere. You might have heard that people will say that, okay, this much ampere current is passing, etc., etc. This gentleman Ampere showed that it is not only on the straight wire like this, but if you make a coil of wire, you make like a coil of wire and pass a current, it starts behaving as if you are having a bar magnet itself. And the amount of magnetic properties, which we call the magnetic pole strength or magnetization that it has, will be decided by two factors. One factor is the current itself, and secondly is the area of the coil. These are the two things which are going to determine about the magnetic shell properties of these coils. And again, how many turns you are having per unit length. So it is the product of all these things that comes what we call the Ampere's law. That is fine enough. That is fine that yes, every charge moving in a coil gives rise to a certain magnetic shell. So immediately the question comes, here we have got the nucleus, and here is the electron moving all around. Now electron is a charged particle. So if it moves around like this, it must be behaving like a magnetic coil. So it must be having its own magnetic properties. So can we explain the magnetic properties of materials with the help of this particular model of the electrons, of the atoms? It was a very intelligent way to check, and experiments were tried. And while experiments were tried, it was found that yes, to a large extent it does. That is, when you put a magnetic field, then there are certain laws like Faraday's laws of induction. This coil, this electronic coil, can have two things. It can shrink because of external magnetic field, and also the electron's own motion might also become faster. So as this happens, the magnetic property of this shell would change, and that is the origin of the magnetic properties of matter. People tried to see all these things, and very good experimental explanation of all these uh, magnetic properties could come about. But there was still a little difference, and that difference could not be understood until there was a very great scientist. His name was Pauli. Pauli came forward and he said, yes, this has a, definitely, this has a contributing factor. This rotation of the electron is a contributing factor, but there is something missing, and that is all called the internal spin of the electron. It is not like the orbital motion, but as if there internally it has got a certain magnetic features inside the electron, and this internal spin is called the spin quantum number. So therefore, every property is quantized, whether it is the spin, whether it is the size of the orbits, velocities inside the orbits, then inclination of the orbits, and now here comes another thing, that the spin of the orbit. All these have to be quantized, and with these, what we determined was the quantum theory of the atom. Quantum theory of the atom is over. With this, many of the atomic properties were understood, but not everything. Because now the question comes that yes, atoms you have understood, things that are inside the atom, electrons moving inside the atoms. But it is not alone that things inside the atom we understand, but we must also understand how atoms join together and form molecules. This also has to be understood. For example, two hydrogen atoms, when they come together, they finally form a hydrogen molecule, H2. How two hydrogen plus one oxygen should give rise to water, that has to be understood. How different kinds of substances are formed, that has to be understood. You know, it is in understanding this that a certain problems came up. Because I will try to explain the difficulties first, and that this difficulty would give you a guide as to how science tries to overcome these difficulties with better experiments on the one hand, and also better thought processes to understand what is happening. Look at this problem, and this problem is very, very elementary for all of us. Here I've got an atom of hydrogen, and that atom of hydrogen has a nucleus inside. It is surrounded by electrons. Correct, fine. Now let me bring another atom of hydrogen. It also has its nucleus, and it is surrounded by an orbiting electron. Now to form a molecule of hydrogen, I must bring them close to each other. And as I bring them close to each other, I know that as I bring closer and closer, there are electron orbits which are in the, or I would say it is like electron cloud, which is outside the nucleus. They are also approaching each other. Now, when the two electron clouds approach each other, both the electron clouds being composed of negative charges, they should repel each other. Isn't it so? So if they repel each other, then they cannot go. They cannot come any further closer. Rather, two electrons, or rather, the electrons in the orbit outside atoms would repel so strongly that no molecule can ever be formed. Two atoms can never come close enough to form a molecule. So what is the problem? In order to solve problems of this kind, the science of quantum theory had to take another step. And that step was called the discovery of a scheme of things, or a new approach to science, and that science is called quantum mechanics or wave mechanics. This is a very complicated field for school level people to understand, and this has to do with the fact, or with an idea, that every particle can have two kinds of descriptions. One is as a particle, and again as a wave. Just as we say, light, all of you know, is a wave. So it has a wave character. But when we are talking of when we are talking of quantum of light, when we are saying that it transfers energy only in definite packets like h into nu, it is as if it is like a particle, as if I've taken a grain of rice, second grain of rice, third grain of rice, fourth grain of rice, and so on. So what is it? What is it? Is it a wave or it is a particle? So this is where a new concept in science comes in, and that is called the wave-particle duality. That every object can have its dual character, and it can have both a wave character and also a particle-like character. This is called the wave mechanics. Now here, a formula for the wave mechanics has to be made, and that was made by Heisenberg, Niels Bohr, Schrödinger, all people joining together and using and developing a scheme of mathematics which was already developed, which in the field of mathematics people had already developed that field, and this field of mathematics is called I will just give you the name. It is not possible to explain these things, and these equations are called eigenvalue equations, eigenfunctions, etc. These had been developed in the 19th century. Now, using those schemes of waves and another class of mathematical entities called matrices, a new scheme of dynamics was evolved, and that is called the quantum mechanics or wave mechanics. Once you put the quantum mechanics, it allows, and when two atoms come from far away and come close to each other, it is true that their external electron or the electrons clouds repel each other. But it also allows a new scheme to come up, that the electron from one atom can jump to another atom, so that what happens in hydrogen it comes, is that when I bring the two hydrogen atoms close to each other, there's a repulsion between the external electron clouds. It is true. But hydrogen from atom number one, or electron from atom number one of hydrogen, can jump to the electron in the atom number two of hydrogen. And likewise, electron from the atom number two of hydrogen can jump into electron. And this is called a sharing of electrons. Two atoms come, but as if they come too close to each other, by certain quantum effects, they forget the distinction whether they belong here or they belong there. It is not like our passports. Yes, if you are a citizen of one country, at least for India, you cannot become a citizen of another country, right? So just as here, duality is allowed, That is when, and similarly, if there be three atoms which have to form ammonia for NH3, that nitrogen and three atoms of hydrogen, they have to form compounds like ammonia. The same thing. It comes only because of sharing of electrons. Electrons on the one hand, they repel, but at the other way, the quantum mechanics allows them to jump from one atom to another, and this is called the sharing of the electrons. So this is a new phenomenon which finally describes the composition of electrons, or composition of materials, and it is because of these we understand that how is a metal formed, how is an insulator formed. The metals are the ones in which the method is such that it is much easier for electrons from jump from one metal atom to another metal. So that if you put a small electric field, it jumps from one metal atom to another, to its neighboring metal atom, and thus an electron can flow. But in insulators, the quantum mechanics tells us that such transfers are far more difficult, and you need far more energy to push them. And that is why certain substances are metals, certain substances are insulators. For example, sodium, potassium, copper, all these are metals, because quantum mechanics will tell us that from the atomic properties itself, that you bring these atoms close to each other and then apply an electric field, it becomes very easy for the outer electron in the orbit to jump from one metal atom to another, so that a current could flow. But on the other hand, if you bring two water molecules or ice and apply an electric field, it does not, because the composition of the ice, as the quantum mechanics would tell, the electron configurations in the ice are such that it is very difficult to strip out one electron from one of the outer orbits and put it into the next one, and then to the next one. It needs enormous amount of energy, so that by a small electric field, you cannot do that. Now, these are the certain basic ideas that were developed, and with these help of ideas, we have metals, insulators, and there are certain other things called semiconductors. What I'm holding in my hand is a mobile phone. It is a semiconductor device, but it is a very complicated semiconductor device, and all the properties that have gone in designing these are based on quantum mechanical properties by which, like a transistor and so on. There are millions of transistors in it, and these are highly miniaturized, but all these became possible only because we have an understanding of the quantum properties of matter, which determine not only their sizes of atoms, the ionization energies of atoms, but also the properties like the electrical and magnetic properties. And that is how this has been made possible. This is a big journey that you have to take from this on. So this is a nice time to stop therefore about the quantum issues, which you will develop as you go to higher and higher classes. So
Thank you. Can I ask you a question? Can elementary particles such as neutrons stand on its own, like neutron stars?
yes, these are also quantum. These are also determined by quantum properties of neutrons. So yes, it is a star full of neutrons moving around everywhere. Okay. This is also an elementary particle. It is a star where neutrons are moving around. Now, how a neutron star is formed, that is also what I have told you about white dwarfs, how white dwarfs are formed. These are also because of certain quantum properties of matter. Quantum mechanics plays its role in determining both the stability of neutron stars or also white dwarfs.
Why can't we make a neutron star in labs?
We cannot make, because its density has to be too huge. We cannot have so much energy. So we cannot create such huge densities in our yes, I have forgotten the amount of mass that you require. Amount of mass should be roughly of the order, I've forgotten, but it is if you read up, you'll you'll understand that to create these kind of conditions, you require a huge amount of mass and huge temperature. So by just bringing a few neutrons here and there and putting them together, it is not possible for us to create or simulate a neutron star conditions on Earth. That is why we cannot make it here.
Like, can there be a proton star, or like that can't be possible? Only a neutron star.
When inside the neutron star, the protons also are there. But when we talk of its neutron star because its stability of the star is essential. You see, whenever we have a star, by its own gravity, it is pulled inside. All right. If it is pulled too much, it will collapse. But can it stabilize? And what leads to its stability? And it is some of the properties of the neutrons, which are quantum properties, which we cannot go in here. It is because of that stability is maintained. It is not that there are no protons there. Protons also are there. But finally, the stability of the star is determined by some of the properties of the neutrons, which are there in what I would say, number density. That is, number of neutrons per unit volume are too huge. And because they are too huge, certain quantum properties come up. And that determines the stability of the star. It has protons too, but the stability is determined by some of the properties of neutrons. That is why they are called neutron stars.
So I've heard that in protons there are things like quarks. So
Yes.
they've discovered those smaller particles. How did they do it?
So this comes to another area of quantum physics. This is the physics of elementary particles. And that we are not going to get into because this is a far more complicated. But yes, there are quarks, and all these elementary particles are determined in terms of the combination of quarks. Proton is one such. Okay.
And are there quarks in electrons?
All are composed of quarks. Okay. But in order to determine, we could not isolate a quark. We could isolate an electron. We could not isolate a quark. But given certain kind of properties, we know how these are composed of. And though we cannot see the quarks themselves, but if the quarks are in this combination, this is going to be the property of the proton. And that is how we believe that, yes, there are quarks. Okay, this is all indirect evidence.
So I think there's a question on the chat. Omkar, do you want to ask?
Is there anything smaller than quarks?
Till now, we don't know. Till now, we have not even seen a quark, but there's nothing smaller than this.
Okay.
The question is, when will we see a quark? We don't know. We have only indirect evidence.
In the periodic table, there are 118 elements, and can we make like more elements?
Yes, but these elements are going to be unstable.
What's the limit?
There are certain very quantum properties which tells us that these are going to be real stable elements are only 92. Only 92 elements are stable. Other elements are artificially created, but these are all unstable elements. Naturally occurring stable elements are 92.
Thank you.
Thank you, please.
By unstable, what do you mean?
That means you create them, but sometimes they will remain like this, like those elements, and then later on, after some time, their nucleus will break. And as the nucleus breaks, you no longer have the same element that you had created.
Oh, okay. Thank you.
Okay,
They're
these are
radioactive, right?
yes, they can become radioactive. Radioactivity is one of the things that can happen, but on the whole, these are going to be very short-lived elements. Very short-lived.
What makes it 92? The like, why would it only make it stable until 92?
There are quantum mechanical issues in it. This we cannot explain just at the level of school. There are 92 stable elements. You can ask why 92, why not 192? Yes, all these questions that you are asking today are very, very important, and very nice that you have these kinds of questions, which will help you to develop yourself further. But answers at this stage will not be possible for you to understand. So you develop yourself with these questions, move ahead, move further, whether it's a question of quarks, whether it's a question of neutron stars, why we want to make them on Earth, and why there are only 92 elements. These are very important questions. And I'm happy that all of you are bringing questions of this kind, and it shows that you will be able to move ahead, or you have an interest to move ahead in science.
I really enjoyed your lecture. Thank you.
Yes, thank you. So therefore, this is, I would say, as far as I'm the end of our series. Maybe next week we will have some revision questions.
Definitely. I think we should like have another discussion on just like the quantum, all the concepts that we discussed and how, like things came to be from start to finish. So hopefully like next week you all can join and we can have that discussion, right?
A revision
I'll also see how we can share the videos, so those can be made available to you, the recordings, and you can listen to them, and if there's any questions, or you can also revise what we discussed in the previous sessions.
Thank you all. Thank you very much. Thank you, please.
Any other last questions before we close for today?
How can I get the recordings of this class, today's class?
What's that?
A recording, this class is.
Yeah, that's what I was saying. I will just like discuss with Lakshmi about how we can share. I think we'll just make them as videos available to everybody. Okay. So let me just post that on the group. It was being recorded. I think I started recording probably after the first 10 seconds of you speaking, Professor, because I just remembered. But I think, yeah, we recorded most of it. It should be available, and I'll share that information on the group.
Thank you, please.
We'll go through it again one more.
I agree. Like, okay. I think like before we meet next week, I think you all should go through it again, because there was a lot of content covered in the last 3 sessions. So I'll just find out and I'll try to share it within the next 1 or 2 days.
Okay. Thank you.
Thank you.
Thanks a lot. Thank you, Professor.
Please. Thank you, please. Thank you. Okay.
Yeah.
Bye. Bye.
Bye.
All right. Thank you all. Bye.
Thank all of you.
Bye. Have a good day.
Bye. Thank you.
Bye.
Bye.